well, after a coffee or session or so for the ECT Star workshop on the mass in the standard model, consequences of its emergence. And we have two talks in this part of the session. It's on the prospects of emergent mass and structure studies at the EIC by Rolf. That's the next talk. And then afterwards, a talk about accessing the erosion of the nuclear mass, and then some discussion. So we will start with Rolf's talk. Rolf, if you could please share the screen.
Okay, there we go.
So we see you, but not the screen yet.
It's because there's too many windows always.
All right.
If ever I can find it. Where is it? 1 second. I have too many screens always. Okay, now you should see it.
We see it, yes. Yep, still see it.
Okay, so yeah, it's always a pleasure to talk at the ECT Star. And I'll start with a little anecdote. It's like when you're in the circus and you have half the time you have the buffoons. So you get excellent talks, more or less, from Van Keun, Sinead, and I'm sure that Castal will the same. And then you have the token experimentalist in there for the halftime buffoon show. So that's how I feel. So this talk won't have as much rigor as my theory colleagues, but hopefully I'll bring up some interesting things forward. So let's take a little bit step back. So I will talk a little bit about the proton, but mainly about the pion and the kaon structure and mass. So we know the visible world, the world we see around us, is mainly made of light quarks. And if you more or less take the nice little diagram our colleagues in Heinrich physics show with Higgs in the center, in reality it's these particles, the gluons, the up, the down, and the strange, which make most of our universe, makes our mass, makes our structure around us. And it's really the nonlinear interactions of those quarks and gluons which cause a lot of our mass, emergent mass and structure. And it's quite a variety. You've seen the whole spectrum earlier in Sinead's talk and the exotics, what can all happen. But even like the simple systems, the proton mass quark structure is pretty simple, up, up, down. Its mass is about 1 CeV. We do know that most of its mass is generated by dynamics. We do know that if we look deep inside the proton, you see a huge amount of gluons, which is kind of a telltale about these interactions. On the other end, the world has left us with a pion, which is simple structure you can imagine, an up and an anti-down. 140 MeV. Now, the pion only exists if mass is dynamically generated. And I'll come back to it a bit later. There are questions, and this is kind of a weirdo question, but I'll come back later. We actually don't know how many gluons there are in the pion. Same with the kaon, mass about halfway between the pion and the proton. Has some similarity with the pion. It's essentially the same as the pion, you just change the down quark by a strange quark and you're done. And what you'll find is that the kaon is really a boundary between emergence and Higgs mass mechanisms. There are questions similar, like simple questions are how do the gluons look like in a kaon? Are there more or less than in the pion? And I'll come with some controversial statements later on because people have different opinions. Now, in the end, for the EIC, through the proton, it will allow to an intermediate contribution to the proton mass, the so-called QGD trace anomaly. I'll have a few slides on that. You'll get to hear more about that in the next talk. And for the pion and the kaon, I think the EIC will really be groundbreaking because it will allow more or less to learn quite a bit about the structure of the pion and the kaon, and in particular also, for instance, measure its structure functions. And that's done by the Sullivan process. So let's go a little bit back in the Yellow Report. Most of you will know what the Yellow Report was an exercise initiative of the electron ion collider community to write down more or less their science and the detectors it leads to, the requirements for the detector for the electron ion collider. And if you go to the executive summary, page 10, you'll find a little bit that the EIC can play an essential role for a complete understanding of the proton mass by essentially determining experimentally the contribution of the trace anomaly. And you also find that another way to address the emergence of hadron mass is through chiral symmetry features that manifest in the lightest mesons, the pion and the kaon. So I will start a little bit with the proton, but I mainly will go into the pion and kaon, because I personally think that that's where we can learn most about the emergent mass and structure. And for some that might be counterintuitive, because these are the Goldstone bosons, but I'll try to put that a little bit in perspective. Now, this is a topic which have really become very in fashion the last 5 years. Proton mass workshops, there have been 3 of them, 2016, 2017, also the ECT STAR. A recent one, 2021, hosted by Archon, and there is an INT program scheduled for this, which was postponed by COVID to later this year. Now, again, the first quote is more or less directly from the long-range plan in the US in 2015, that the majority of the nucleus mass is due to quantum fluctuations of quark antiquark pairs, the gluons, and associated with quarks moving around at close to the speed of light. And indeed, and that's in 95, G made a sum rule. If you more or less make a mass sum rule for the proton, you can see there is a piece more or less from the quark masses, a piece from things are in motion, the quark energy, the gluon energy, and a piece from the trace anomaly. And at that time, Chi postulated that, okay, the quark mass is small, and he came that the trace anomaly contributes about a quarter, and the quark and the gluon energy is about equal, and about 3/4 if the quark mass is small. Early lattice calculations did this kind of pie chart, and even if you go very recent, Konstantina Alexandru, if you look at the numbers here, what she calculated or what they calculated, it's actually very close to this pie chart. So this is roughly what you see. And again, the 20% of the anomaly is not too far off from what G at that time had, more or less. Now, what does an EIC contribute there? One way to more or less measure this trace anomaly is essentially to turn some diagrams around. So you try to model the anomaly around. So you do photo production with a heavy quark system. And you see this, and with some imagination, this diagram resembles a little bit anomaly. And then by more or less determining things at threshold, you can, same as lattice, we can determine phase shifts. And by that, you can more or less infer information about this trace anomaly. So you do that by the different NHCs more or less close to threshold, measuring these T distributions, and that essentially will constrain it. Now, that being said, at low W, say for instance here, where these data are, you get best constraints on the trace anomaly. And of course, if you go to larger W, you get more and more sensitivity to gluons. Now, this comes directly from the yellow report. This is kind of a picture how well more or less you can constrain that trace anomaly, be it by Yape psi production at 12 CV, and this is from solid, this is from whole D, this thing, or from with the heavier particle, the epsilon production at an EIC. There are some pluses for these heavier quark systems, so it's always good to have different heavy quark systems. And you see it a little bit, isn't it? How well you can constrain this trace anomaly. And you see also that these data are all around 25%. So that's one of the main aims for the EIC, more or less to constrain this trace anomaly. And again, I'm sure you're going to hear more about that in the next talk. I'll mainly talk about pion and kaon structure. And again, my belief is that's where a lot of the emergence of mass and structure, which we deal with in the world, comes from. Similarly, a long history. There have been workshops hosted for the last 5 years all around the world. Same here, you see more or less, there was a workshop, the ECT STAR in 2018. That resulted partly in a white paper for the EIC in 2019. There have been follow-ups, workshops, also with Amber. You're going to hear about that tomorrow. And this is our remote workshop, and there's another workshop hopefully in 2022. Just recently, we had the yellow report and another article accepted in Journal of Physics on the structure of pseudoscalar mesons, which shows you a lot, actually, what I'll show you in the rest of this talk. Now let's take a step back. Let's look actually at these Goldstone modes. I often hear, well, the pion is different, it's a Goldstone particle. The kaon is different, it's a Goldstone particle. That's nice to hear, but that's a null answer. Yes, I know they're the Goldstone particle. That still doesn't tell us about their structure, why the pion has similar radius more or less as the proton, and the kaon is smaller. And it doesn't tell us why it says these masses are what they are. It gives insights, but doesn't tell us anything. So it's a null answer. On the other hand, it does give you a sense insight. You can more or less folding in a chiral perturbation theory, you can get constraints more or less, and you find indeed this issue that the mass of the pion squared is kind of linear here in the quark masses. This is of course different than if you go to the normal constituent quark model we were dealing with. So pseudoscalar masses are generated diametrically, and if you look at this formula, you see that m pi squared is around the square root of the mass. So that's already a bit weird. And that means that the mass of the bound state increases as with the mass of constituents. And it also shows you a little bit that often when you talk about the constituent quark model, and those of us like old timers like me, when we did the mass formulas for different baryons and mesons, we happily also neglected the pion decaying because they're constant bosons. But again, it's not an answer. So if you would actually do the constituent quark model, you find out that your constituent quark mass is about, it doesn't work. So it's not real. And I'll show you later that in both Dyson-Swinger equation and lattice, what you find is that you find the mass function of the quarks or of the gluons, and it's similar. It doesn't matter what hadron the quarks reside in. If you go to very short distances, you have a quark on a gluon, it just pulls the gluon fields around it together. It's kind of the same as Higgs, it's a drag force. It pulls these things around, it makes constituents. Doesn't matter what particle it's in. Who cares that it's a constant boson? Who cares what hadron it is? So it's actually the dynamical chiral symmetry breaking that makes the pion and K mass light. Now I'll come back to that. I'll call a big back and forth here because I tried to put some questions in your mind for the theorists. And again, this is an experimental view. Okay, let's go a little bit to this. Let's look at the chiral limit and let's assume a Parton model basis. Now in that, you can directly write down that the proton mass is entirely related to gluons and due to the trace anomaly. Same in the chiral limit for the pion. It doesn't exist. The mass pi squared is 0. Sometimes people say, well, that means in the chiral limit, the gluons disappear and contribute nothing to the pion mass. This cannot be true. Quarks and gluons still, as I just argued, dynamically acquire mass. This is a universal feature in hadrons. I just had it on the previous slide. There's also interpretation that in the chiral limit, the pion's gluon structure becomes more like that of the vacuum. Now, that might be true, but that's the chiral limit. In reality, the pion mass is 140 MeV. That's not 0. So you can ask the question, what gluons are there in the pion? Are they like the vacuum? Are they different? And I'll show you a little bit. I'll put some questions up. So the chiral limit gives us understanding and can act as a consistency check, but the pion mass is not 0. It's 140 MeV. So I follow a little bit slides from John Wei, we will talk later. If you do a mass decomposition, it should not only work for the proton. It should in principle be valuable for the proton, the pion, the K, and we want to globally understand the emergence of mass. And again, that means in these kind of matrix elements that you have to understand the mass of the proton, the mass of the pion, and the mass of the K. And similar, you can argue that such a decomposition is only valuable if you can measure it or calculate it with comparable approximations. So this comes a little bit, this is why the pion and the kaon, in the end, we want to measure the proton. We want to understand the mass gap to the proton, but we have to also understand where the structure and the mass of the pion and the kaon come from, even though they're constant bosons, and that makes them actually more interesting. So if you do the same, more or less, you say the pion mass is not 0, it's 140 MeV, you go back again to the original Jeep article, and he just redid an article. And there you would find that in this article, the pieces of the quark mass is about half the mass. The piece of the anomaly is about an 1/8. And then you have similar contributions of the quarks and the gluons. So in his picture, in the chiral limit, all terms vanish and the pion's gluon structure becomes like the vacuum. So that's similar to G95, and you see the same here. Now, there have been people also have done calculations. If you look at Young et al., and they essentially find, and this is kind of interesting, and I think these are lattice calculations, that essentially they find that the combined quark-gluon energy is completely different for a pseudoscalar, where the constant bosons are, and a vector meson. And you see kind of it goes to 0. So the combined, it goes to 0. On the other hand, so you can say that's the same as G at here, all terms vanish. On the other hand, if you look at GR, for instance, in 2D QCD, yes, they go to 0. That's because two terms essentially cancel. And if you add them up together, you still find out that the Kalman-Oak-Renner relation holds, which it should. in the chiral limit. So let's go a little bit back. So the context of what I'll show for the rest is, and again, these were just to pick some questions. I'll come back to it later. Why essentially people sometimes say, well, you do measurements that have nothing to do with mass. Well, they do, because they give us the understanding and the interpretation. They also find where certain interpretations are wrong. So much work, what I'll show you later, is done by a large group of theorists and experimentalists. Many of them are actually either organizing or sitting in the audience here, so they'll know better than me. We wrote an EIC white paper. We have a subgroup of Mason structures, part of the EIC use group yellow report initiative, which has kept on going because it has been very successful. There is a recent EIC related paper, which emphasizes mainly the synergy between experimental theory and lattice to understand these emergent pion and KN mass and structure. And it also, interestingly enough, drives the forward detection method at an EIC and the integration. And I'll show you a little bit of the cartoon, how people see models. In the end, all these things have to go together. Theory, lattice, experiment. And we want to start making understanding in our interpretation. So to go to mass in a different way, let's look at mass without mass. This is known from Dyson, Schwinger lattice results. So you essentially look at the clue interactions. And again, there's people, Christian, Greg, others who are much more expert than me. But what you find essentially, and that's the same for Dyson, Schwinger and lattice, that if you more or less are in this frame and you pictorially have some quark mass, you slowly put it at rest, which you can't, but that's what you do. You see it starts acquiring mass as an effect of the plume cloud. That's true in lattice, that's true in Dyson, Schwinger. And that's partly why we say, well, look, the mass of the visible world comes from the quark-gluon interaction, and the Higgs mechanism hardly plays a role. And because the Higgs mechanism might be relevant here, but its mass is much bigger, it wins. And this is, of course, true for not just the light quarks. It's also true, like here's the light quarks, also true for the strange quarks and heavier quarks. What you also find happening, and if you look at the strange quark system, it has some mass already by the Higgs mechanism, but it's about half the mass. It also gets half of its mass from more or less this emergent mass mechanism, this quark-gluon interaction. So it really is, it's at the boundary of emergent mass and Higgs mass generation. So that's why we like the kaon also. And this comes in this picture. You can define also your mass budgets. And here you more or less see that you can define it here as terms of more or less the current mass of the quarks. And this comes from Craig Roberts and others. And you see that for the proton, there's hardly any current mass contribution. And there's quite a bit more or less of the chiral limit. And some essentially interference between the mass mechanism and the Higgs mechanisms. Why on the other way around? It's the quarks, very small. And a large part is just the interference between the Higgs mechanism and this emergent mass mechanism. And again, is somewhere in the middle, because you already have a piece of the Higgs mass coming in there. Or the Higgs mechanism giving the strange quark mass. Let me say this correctly. Now, and again, these are not directly measurable, but what we can do is find the effect of these kind of mass mechanisms on observables, or not directly observables yet, ingredients, I should say, of our observables. One is pattern distribution amplitudes. This shows you, again, the strong synergy with lattice, and we then might talk later about that this week. And it shows you a little bit that lattice and essentially that, where do I say that? That if you start more or less making your quark heavier, you see this guy getting essentially, what do you call it, more peaked in the center, more its asymptotic form. And if you have a light quark or light pion mass, it gets very broad and concave. And that I say essentially here. Or you start looking at more or less the kaon, and you find more or less that this guy is not completely symmetric around axis 0.5. So that's the effect of this Higgs mechanism. So these things start getting not symmetric in the pattern distribution amplitudes. And in the end, that's going to have impact on the observables we calculate. Say more or less, to come back to that a little bit, if you look more or less this emergence versus the Higgs mass generation, and this is done also more or less from one of the articles, and you see the same kind of thing. You see the different curves more or less. The emergent mass is dominant for this A, this broad concave pion function. And if you look more or less here, if it's primary Higgs mechanism, well, this PDA starts being more or less more peaked and more centered. Yeah, so in the limit of infinitely half quark masses, the Higgs mass overwhelms the other mass generating forces. And you saw that earlier already from this mass acquiring curves for the the up quark, the light quarks, and the strange quarks, the B quarks. Unfortunately, again, experimental synthesis of the exact PDA form are in general difficult. So all we can do is more or less do observables which have this PDA embedded into it, and then try to derive information out of those observables to get insight. Now, people have tried to more or less to say this is not science fiction. This is a self-consistent calculation. What people try to do is affect a little bit the different mechanism of this emergent mass mechanism, and what is, for instance, then the impact on an observable. So here's two different mechanisms on this mass acquisition, and here's the impact on the pion form factor observable. And you see what happens is that the height of this form factor times q squared start changing. So there is a direct correlation of the form factors and these PDA mechanisms. So empirically, at least, we have some tools, some insights. So to give you one example, this is pion for the prospectus EIC. And you see more or less these data points, more or less, this is from the older article because nothing changed in reality in later work, up to about q squared 35. This is done a little bit different than normally. If you assume the Sullivan process, that's the same as more or less in the regular measurement we do it. But normally what we do, we try to do an LT separation to isolate the pole term, which is dominant more or less, the longitudinal cross section, which is dominated by a pole, which gives you most access to the pion form factor. What we do in this case, we measure the pi minus and pi plus ratio. Again, if the pole is dominant, this ratio is unity. If it's not unity, then there's other terms coming in. So it gives you insight on the form factor. So that's what we do in this case. And at the moment, we're working on the same trick, more or less, for the Kn form factor, by trying to see whether you can get that from the ratio of lambda over sigma. That's tricky because A, we need insight from 12CV data. B, now you need in a high energy collider to pinpoint down whether your particles came from a lambda or a sigma, which is non-trivial. But that's what we're working on. It's not impossible. So that's, again, is done by the Sullivan process. In the end, what you're doing there, you're scattering from the nuclear meson fluctuation and try to pick out this meson. So the way that works experimentally is you measure, you detect your scattered electron. And if you want to detect a pion or kaon, you detect neutral lambda. And then you might measure either a pion if you want to measure the pion form factor, or you measure X if you want to measure a structure function. There are some uncertainty, which is called the flux factor, that essentially means how much of this fluctuates into this pion. That has to be constrained either by theory or other measurements. In comes, for instance, Amber, compass measurements. Jan will help you there. So, but that's essentially what you're doing. That you can do it at an EIC, I'll show you a little bit here. It shows you more than you don't have to, okay, many of your theories, you don't care. It shows you in the different ranges of the energies for an EIC, whether it's 5 on 41 and 10 on 100, where the particles go. One thing you directly can find happening is that this scale is completely different. Here's like 0 to 140 degrees, and here it's around 1.5 degrees. And that just means that the scattered electron goes into your main detector, and this leading neutron or whatever it is goes forward around your beam pipe. This is why we had to pay so much attention to the forward detection. It always goes forward, but you need to measure it. That comes a little bit here. So this whole cartoon of the forward detector of EIC, a lot of that was driven by meson structure. Because another thing which happens, if you now want to look at kaon structure, the lambda and the sigma decay. So somewhere you produce a kaon lambda, it lives for some time and it starts decaying. Well, if it decays, it might hit the inside of your beamline elements, but we still want to measure them. So these detectors around here, and this guy too, is a sense to make sure you can tag whatever came from this kaon or the lambda. There are some benefits for this at lower energies, especially for the kaon structure function, and that just has to do that if you boost your energy to infinite, the kaon decays well beyond any of your detector, or the lambda decays well beyond any of your detectors. And then there's no way you can separate the lambda from a neutron from a sigma. It just doesn't work. But essentially, the main reason of this slide was this kind of forward detection needs was driven, for instance, by the access to meson structure, the Sullivan process, but there are also other processes. Now, the one thing to keep in mind in the EIC is that you have a very versatile machine. You can scan its energies, and you have huge luminosity as compared to here. And the only other electron proton collider we had, the luminosity of an EIC is of order 100 to 1000 times here. The detection fraction is also much better, and that's because we make this beamline from the beginning, and that has to do also that the energies are low, you can do it. Okay, but you still now more or less have a low thing. The fraction more or less that you have this pion nuclear fluctuation is small, and you can see that a little bit in this graph. It's of order 10⁻³ for a small bin, or 10⁻² if you have a larger T-bin. So well, that kind of balances this. So what that tells you is that for a pion, if you can do this Sullivan process, or for the kaon, if you can do this process, you can get similar structure function data as the vulnerable proton structure function data here, which told us quite a bit. And in fact, are still the drivers of the PDFs around the world. So it's actually very powerful if we can do this. Of course, the trick is, can we really isolate that we're measuring from this near physical pion? And that's why we'll do measurements over a large range of T, and more or less really say that the answer we get is T independent. We say it like that. And that means it's like an on-shell pion. So this shouldn't tell you too much. It just shows you a little bit, integrate over T, more or less, what the quality of this structure function is if you can do it. And you know, okay, this is a structure function that uses 60, 120, 240, 480. The main thing you see, very small uncertainties. So the structure functions we can nail. Of course, the fact that it starts growing at large X is standard, isn't it? That's true for any structure function. This has to do with your pattern distribution functions die at large X. So, but you can see already visually, I like this plot because visually it tells you you can do stellar structure function measurements in EIC if you can utilize the Sullivan process. And then you can more or less say, well, that means, and this is the impact most EIC has, and again, Patrick will say more about that later, I'm sure. If you can do this structure function measurement, that shouldn't surprise you either. You can constrain the quarks and the gluons, the C, the valence separately, and you see you get a stellar improvement. And this is where the statement comes from. If you build an EIC and you do the pion and the kaon structure function, you get kind of a proton structure function quality data for the pion and the kaon. And you can really nail down all these pattern distribution function and also the gluons. And you see that here a little bit, isn't it? The gluons is red, very well constrained down to low X. So this rise, this infinite rise of the gluons at low X, we will find in the pion and the kaon too, and I'll come back to it a little bit. Same we can do as function of T. Again, you see very quality data. This is kind of a text structure function. It's not a very good observable. It's not very well defined, but let's assume it's a text structure function. Main reason why I show it essentially is that we can also get very high quality data to around T is 0.6. This is where we believe we will get good enough data constrained based on theoretical arguments that we can really get the theoretical uncertainties under control to make sure it can still be extrapolated to an on-shell pion. So that's where this magic number comes from. And you see excellent error bars. And I'm sure Patrick will later talk more about the impact as a function of T also, how well you can improve more or less your uncertainties. Let's take one step back. I have this one in there. I don't always show it. This is for the kaon structure function at large X. And this comes back to one thing. If we actually do phenomenological arguments, many people believe there's less clue in the kaon than the pion. And this comes back to a little bit the warning side earlier. If you say the pion is like the chiral limit and the pion looks like the vacuum, now we're going to start saying that the kaon has less gluons than the vacuum. Okay, that you can say that, but it starts getting very difficult. So you see, you find all kinds of questions. So what the main reason is just what I try to have this slide in there. We want to measure the gluon distributions in the pion and the kaon. Now, maybe apart from the link, more or less, how much average energy there is for quarks and gluons, the link with the mass sum rules is tenuous, but it does give us directly interpretation what happens in the pion and the kaon and what happens later in the proton. But you can see the error bars are pretty good for this ratio of the up and the quark and the pion and the kaon. I'm sure you see similar things from Amber later. This is a hot topic, but it comes back to a little bit. We really don't know how many gluons there are in the pion, gluon PDFs in the infinite momentum frame, or in the kaon as compared to the proton. This you got to measure. Now, if you can do this Sullivan process, there's much more you can do. You can measure this pion structure function over a large range of X and Q squared. You can see more or less what are the quark and gluon energy contribution to the pion mass. And this is in this mass sum rule. So say it like that, isn't it? It's not the leading twist mass. It's in that sum rule. Is the pion full or empty of gluons? Are there more or less gluons in the kaons than the pions? what are the quark gluon energies to the kaon mass, and these are kind of then the measurements you need to do this to tag more or less that solvent process and what energy range is best to do it. And you can go beyond that. You can measure the pion form factor, I showed you that, which gives you again quantitative guidance on the emergent pion mass mechanism. Again, that doesn't help you to have the highest energy, but it tells you a little bit where we can do measurements. Same for the kaon, which actually likes lower energies because you have to be able to measure this lambda over sigma ratio. But you can do more. Let's go. You could, in principle, also, if you truly can convince yourself, you can utilize this solvent process. You can go one step beyond. Well, we could think about, speculate, can we even do semi-inclusive or deep elastic scattering of a meson target? Well, if so, then you can do the same as for the proton. Then you can determine the trace anomaly contribution to pion mass. So that is in principle not impossible if you can convince yourself that we have 10 years from now the mechanism, the theoretical tools, the experimental tools in place that we can truly convince ourselves that we can go from an off-shell to an on-shell pion, essentially. And they do the same. You can DVCS, you can also do transverse momentum distribution in the pions and the protons, and you can see whether they are universal. And again, if you go back to the old Lund origin Monte Carlo, where a lot of the TMD effects came from kind of tunneling to the flux tube to the vacuum, they could be the same in any hadron structure, and we don't know. So in summary, I think, look, we got to realize that protons, neutrons, pions, and kaons are the main building blocks of nuclear matter. If we truly want to claim we understand hadron structure as relevant for the visible world, we have to understand at least the pion, kaon, proton, neutron, and likely lambda at the same level. We can say the pion, kaon, are Goldstone bones, they're different, but in reality, we still want to understand why they came with a certain mass, why they came with a certain radius, why they came with a certain quark gluon structure. Same as for the proton. In that sense, they're not different. And likely maybe the lambda, because we do know more or less that the strange interactions have an impact on our visible world also. I gave you only some snapshots. Paradoxically, these lightest pseudo-Kähler mesons could be the key to the better understanding of the emergent mass and structure. And that's partly just because they're better calculable. And the effects might be more interesting in these very light pseudo-Kähler mesons because you can see the effects of the PDAs or the PDFs coming in. And again, yes, they are the number of Goldstone bosons of motive QSD, but that essentially makes them more interesting. So unlevering that particle structure, the interplay with the Higgs mechanism, mainly through the kaons, is a common call of theory, phenomenology with quantum QCD-based approaches, lattice, and just global analysis of particle distribution. And you're going to hear more about that later. And of course, we want to link that to experimental measures because our field is experimental. We don't believe anything unless we have an experimental measurement. The unique role of EIC is to access pion and construct over making use of a versatile large center mass range. I think the EIC will have the final word on the contribution of gluons in pions and kaons as compared to protons. And again, we don't know. Settle how gluons persist as few, how and if gluons persist as viewed with high resolution, and just vastly extend the X and Q squared range of the pion and kaon charts and the meson structure knowledge. And then I'll just stop with a smattering of the role of the EIC, which both more or less for proton threshold production of heavy quark systems, constraining the anomaly, or with the Sullivan process measuring form factor structure functions and impact on particle distribution functions. Thank you.
Thank you for this nice overview, experimental overview of the hadron mass. Yeah, so any questions? I don't see any hands raised. Guess it was very clear.
Yeah, I should say back some slides came back on when there was earlier this mass workshop, big discussions among the theorists, what they thought they knew and didn't know, and I tried to capture that a little bit in the slides. And I think it shows that people might think they know some things on pion and kaon mass, but it's actually, there's still a lot to learn. And I don't think any of the pictures is right. So
I'm not sure I can raise my hand, but I do have a little question. Can you hear me?
Yes, please go ahead, Craig.
Okay, I'm looking at the image in the middle panel at the top there, Rolf. This J-psi upsilon production, it does seem to rely a lot on vector meson dominance being an appropriate tool for analyzing the experiment. How reliable can that possibly be when, at least for the J-psi, you're 10 GeV squared away from the mass shell when you get to photo production?
Yeah, I don't believe it relies on vector meson dominance. Again, maybe Gustavo can say it later. I think people have more or less done all kind of calculations. It does rely on the two gluon exchange mechanism, as far as I know. I don't believe it relies on vector meson dominance. It does does rely on this thing, isn't it? That it's truly this two gluon exchange mechanism, as far as I know.
I think Gaston will probably address it. So perhaps after Gaston's talk, we can come back to this issue. That would be fine with me.
Yeah, I mean, that's probably more a question for him than for me.
Okay, yeah, that's fine. We can discuss it after the next talk. Any other quick questions? I guess we have to move on to keep on schedule somewhat. Okay. Certainly we can discuss then after Gustavo's talk. So thank you again, Rolf, and